3 sine x equals 0 in value. And there are 7 locations where that occurs. There's 7 locations where that occurs. And so, okay, all right. So they've got the next segment going. So let's go ahead and get rolling here. So what I did in the last segment is I gave you a very brief introduction, and we actually did a vector or actually a problem solution back earlier in the course with most of that time. Now let's get on into the vector algebra and the associated graphs. Okay, let's come back to where we just left off a moment ago. We've seen how to represent a vector with a component that is what we oftentimes call, it's a part. We break it into parts that are perpendicular to each other. When we write a single vector, we oftentimes write it with parts that are perpendicular to each other, and they're called components. This is called your x component, and the other part right there is called your y component. And I'm going to show you another way in a few minutes on how to write the symbolism for a vector like this. Now, back to the river. How fast is the boat moving? From the previous segment, we're paddling our boat horizontally or straight across the river, wanting to get to the other side at 2 miles an hour. We're drifting down the river at 6 miles an hour. How fast are we really going in our boat? Here's our boat. How much?
6.32 miles.
How'd you do that, Joshua?
Pythagorean theorem.
Pythagorean theorem. It's not hard, right? What you're doing is you're looking for what's called the magnitude. You're looking for what we call the magnitude of a vector, or the vector's magnitude. And what that is the symbol for the vector without the arrow attached to it, or without the boldface type, or without the bar underneath it. In textbooks, you'll see it written where they'll take the boldface type letter for the vector and they'll put double bars on both sides of it. It indicates the magnitude or the speed that the boat is traveling. And what that is going to be, you can see it from the picture here, is the Pythagorean theorem, like Joshua said. It's made up of the square root of the sum of the squares of the components. Square root of the sum of the squares of the components. So in this particular problem then, the magnitude of the speed the boat will travel is going to be equal to the square root of 2 squared plus 6 squared, which is the square root of 40. And we oftentimes want to be able to write down the exact value. So once again, reviewing an intermediate algebra idea, you look for perfect squares as part of what's underneath this radical. 4 times 10, and out pops out of the square root a 2. So 2 radical 10 miles per hour is the speed of the boat, which Joshua said, and you see 40 here, so you know your answer is a little bigger than 6, about 6 point what? Square root of 40?
6.324.
6.3 what?
24.
Okay,
Oh,
about 6.3 roughly miles per hour. But you understand? That's the magnitude. Magnitude. That brings up another topic. A vector has more than one thing associated with it, more than just its magnitude. More than one thing. We also need to prescribe what? What would you expect? Huh? Direction. Doesn't it make sense that we should specify some direction for this thing? I mean, if we wanted to get across the river real quick, it'd be kind of nice if we could go at 6.3 miles an hour, because we'd get across there a lot quicker. But we have to have a way of directing this thing, don't we? So we need also not only magnitude, a vector's magnitude, where there's no arrow symbol on your symbol for the vector. That means the magnitude. we need direction. We also need direction. So we need magnitude and direction when we do vector stuff, vector work. Magnitude and direction. So there's a multitude of ways we could explain that here. Why don't we say that the kind of direction we want to prescribe for this effect, even though our boat's horizontal and we're drifting across the river here, let's look for this angle right in here, that angle theta. That angle theta. And so what you can see is that the tangent of theta from the picture there, the tangent of that angle theta would be 2 over 6, wouldn't it? Reduces to 1/3. And then if you have your calculator and degree measure, you can punch the inverse tangent of 1/3, and it'll tell us that direction approximately. Somebody want to do that? Make sure you're in degree mode. .4. 18.4 degrees approximately? Okay, good. Okay, so notice we have a magnitude and a direction. Okay. That's a brief introduction to that idea of how to figure out vector component. You take the vector components and you figure out what the magnitude is through your Pythagorean relationship, and then you figure out the angle associated with the direction, associated with the appropriate direction based on the legs of the triangle. Not too tough, is it? You've got all the trig skills to be able to do that. Now, what happens if you have more than one vector hooked together or acting on something? So let's come over here.
So that theta value is based upon the your sketch. I mean, the direction you're going in your sketch. I mean.
Yep. Mm-hmm. Now we're gonna, for most of math kind of applications, we're gonna set up our usual x and y axis system. Our usual x and y axis system, and we're going to relate the direction of the vector that we get to those axes. Okay? So here's the way we're usually going to do the math on that. Is we're going to take our traditional x and y axis system, and if we've got some vector sitting here, it's going to have some value, some length, right? Why don't I call it r? Familiar territory. Okay? And here's some theta. And here's some y, and here's some x. And that's going to remind you of what? Last session? Polar, right? Polar. Now, to make this a vector, though, let's make this an arrow. Let's put an arrow on there, indicating a direction of travel. The direction of travel, or a value for distance, maybe. That could be a distance traveled, right? It could also be force, couldn't it? So many pounds of force, right? If I grabbed hold of this spot and I pulled on a rope that direction with a certain force, that could be a force. And that force could be thought of as having a y part and an x part. Pulling, right? You with me on that? Like if I was pulling up with 10 pounds, right? Up with 10 pounds and to the right with, say, 20 pounds, wouldn't that in effect be pulling on this location right here with 10 up, 20 that way, and give us a resultant force that way? Which, what would that be, 110 and 20? What would that be? We have 20 here and 10 there, square root of 500, right? Right, wouldn't that be it, right there, right? So about 22.4 pounds. If it was 20 pounds to the right, 10 pounds up, right? Wouldn't that be the magnitude? And so I could replace the 20 pounds here and the 10 pounds there. I could replace that effect with one rope pulling with 22 pounds at this angle. So R is equal to the square root of the sum of the squares of the legs. That's the magnitude of the vector in general. And notice I have a standard angle here, don't I? Standard angle. That's going to become very important in a few minutes. So use what you've learned earlier, standard angle. Now, the tangent of this angle, standard angle here, is y over x, isn't it? So the angle is going to be equal to the inverse tangent of the y reading over the x reading usually. Usually.
Why is it usually?
Oh, that previous problem, I called x and y, and I actually found something other than the standard angle over there. And it was actually our x reading over our y. You didn't hear that, though. Okay? So it's going to be draw the picture of the vector and then think about where this sits. Now, you also have to have your brain engaged here, don't you? Here's why. What if I instead put this vector over here? And you punched inverse tan of y over x. Y over negative x. It's going to give you that direction down here because of the inverse tangent function. Okay? So always draw the sketch. And when you're doing the direction, always use your brain. Okay? Very important. Okay? All right. Magnitude, direction. Got it? So, let's have some fun. We're already having fun, but let's have some more fun. Okay. Everybody feel okay so far? It's all familiar territory. All familiar territory. We could write this vector R with the arrowhead on it as made up of x and y shown like this. So here is the vector in its representation. Here's its direction, right there, and here's its magnitude right here. You ready to take a trip? Here we go. And let's learn a little navigation stuff while we're at it. Typically on maps, at least in the northern hemisphere, we write north upward on the maps. East, west, south. N-E-W-S, news. Okay, which doesn't exist anymore nowadays in the media. But anyway, enough said on that. Okay, here we go. Let's say we're going north 30 degrees east. We're traveling north 30 degrees east. Here's the way you write it. North 30 degrees east. That should make sense to you. You just read it. North 30 degrees east. That means off of north, you're heading at 30 degrees to the east. Now, how far do you want to go? Travel? We're hiking. Taking a hike.
1 mile.
5
5
miles.
miles. Boring. 1 mile is boring. Okay. 5 miles. And so we've got an angle sitting right here at 30 degrees, right? Off of north. So that means this standard angle here is 60 degrees. Okay? Now we get up here. So we're going to go north 30 degrees east, 5 miles. Okay? Now, let's say we head south, well, let's go, let's go south 70 degrees east and some other distance. How far?
16 miles.
16 miles. So this would be a nice, energetic day hike. Okay? Right? Let's draw it. We're at this spot up here, aren't we? Oh, and let me put an arrow on there, right? See the arrow? That's important. It's a vector. Okay, now, you're up here, and you got your compass. You got your compass with you. And you're now going to go south 70 degrees east. Right? About the direction my marker is. South, 70 degrees to the east. That's the way you would direct this. So we're going to be heading out this way at 16 miles, right? Drawing a picture of this. Elizabeth? You okay?
Sure.
South, 70 degrees to the east, okay? What's the standard angle there from that spot? Standard angle? It could be negative 20 degrees would work just fine, or you could say 20 degrees less than 360, right? Which would be 340 degrees.
Can you walk me through that really quick?
The standard angle, this angle down in here is 70 degrees. I'm not even going to write it on here, though. That's 70 degrees. Everybody okay? That's 70 degrees. If that's 70 degrees, and I want to know the standard angle associated with this terminal side here, this vector, I'm going to sweep from my standard 0 location counterclockwise around 20 degrees less than 360, which is 340. Or I could say minus 20. All right? Very important. So here's the question. We're lost.
No.
Okay? We don't have our GPS with us. Our compass broke. But we know what we did. We know we traveled at this heading north 30 degrees east, 5 miles, and then we headed that direction. Okay? 16 miles. But we do have a radio. So we call our friends and we go, hey, I want to tell them where we are. We need to tell them how to find us. Okay? So here we are lost. Okay. So we want to know from the starting spot what distance we are. We want to know this distance here. And we also want to know the direction. You see? I mean, it's almost horizontal, at least the way I scaled it there. I don't know if that's right or not. But isn't there going to be some distance from the starting point? And so look at this geometry. If you just hook two vectors together as we just did, we form a triangle, an oblique triangle. Which brings us back to something we studied earlier, law of sines and law of cosines. And look at what you know. Side, do you know this interior angle in there? What's the interior angle? Geometry background. Little triangle here, 60 degrees here. Here's 30 degrees right there where my finger is. And this north-south line is parallel to this. So there's 30 in there. And that one over there is 70. 30 and 70 is 100 degrees, right? So we could take a triangle and set it up like this and solve for that side. And this is a side angle side situation using law of cosines. 100 degrees right there. Right? Everybody happy? Familiar territory? So, Pythagorean, nope, not Pythagoras, because this is not a right triangle. Law of cosines, right? Law of cosines. Leg squared over here equals the sum of the squares of the other legs. And you subtract off twice the 5 times the 16 times the cosine of your 100 degrees. The opposite side's angle, vertex angle. Pop that into your calculator as a big square root. And come up with an answer. Did you get it? Make sure you're in degree mode if you're going to use 100 degrees. So big square root, 5 squared plus 16 squared minus 2 times 5 times 16 times cosine 100 degrees. And store that in alpha r. And I would encourage you to draw a scale drawing. And a little more than 17.5 miles. Does that feel right? Does my drawing look relatively accurate? No, it doesn't. If that's 5 between my finger and thumb, 5, 10, 15, 16, and does that look like 17? Okay, I'll tell you what, I'm going to trust that value for a moment. I'm going to show you another way to do this. All right? Did anybody else get my answer? Everybody else got that same answer? Okay. So it seems something's fishy here. Either my drawing's off or my calculation was off. So let's do it a different way. The reason I want to do it a different way is it's actually a more powerful way to handle vectors. What if I took and had, say, 2 or 3 more legs on this? Wouldn't this get much more complicated? Let's say we traveled from this point and we went some other direction, and then maybe some other direction, and then finally, where are we? Do you see how complex it could get if you add more than 2 vectors together? If you just have 2 added together, it's not going to be too bad. You could do the drop back and use your law of sines or cosines on it appropriately. Okay, so here's the way you do it in a more powerful vector algebra form. Vector algebra. We write each vector. So let's call each vector, let's call the first vector vector A, and the second one vector B. So this would be A, this would be B. Those are magnitudes, no arrows on them, notice. And this is the resultant, it's oftentimes called the resultant. And we don't call it a radius anymore. And these are the magnitudes, which we just ended up coming up with, which I think we've said was around 17.6 miles, okay? So here's what we want to do using vector algebra. Our resultant vector is going to be the sum of these 2 vectors, A and B, added together. Notice the arrowheads. Very important that you have those. It's also extremely important, if you wrote this down without those arrowheads, I would say I would be interpreting that as the distance from the starting point would be equal to 5 plus 16. Is that right? No. 5 miles plus 16 miles, that's not how far you are, because you're not traveling in a straight line. Okay, so be careful. If you're writing a vector, always put some symbolism on there, because you'll get a lot of red ink on your paper if you don't. Okay. If you jump into a physics class or an engineering class or something where you're using vectors, or you're out in the woods, okay, anyway, use the arrowheads, please. So, how do we write this? Okay, watch. You're going to love this. You all have this picture in your head, don't you? Right? Everybody's got this in their head from early in the term even, and the polar stuff more recently. So how long is vector x right here, or length x, in terms of r and theta? It's the cosine, isn't it? Isn't it r times the cosine? Right? And isn't the y part right there r times the sine? So if I go back up to the problem here, and I took that first vector, that 5-mile vector at 60 degrees, how much of that is east? 5 cosine 60 degrees, isn't it? East directed part of the 5. How much of it is north? 5. Help me. Isn't it? 5 sine. Okay? And remember what I wrote earlier. I showed you how to write vector components. So this 5-mile leg is made up of 5 cosine 60 degrees is the x part of it, and 5 sine of 60 degrees is the y part of it. The vector components. And I need to add to that vector A. And notice what I'm doing. I'm laying them one above the other. And then what about the 16-mile leg? Think about it, folks. Look at this 16-mile leg here. How far to the east do you travel with a 16-mile leg? How much is this between my fingers? I think there's some confusion. Is there confusion? Anybody confused? What are you confused about? Not even sure. Okay. Go back to the boat, right? You've got a certain speed you're moving across the river. You got a certain speed you're moving down the river. They're separate, aren't they? They're separate. If the river wasn't flowing, you'd just go at 2 miles an hour straight across the river and land on the other side, right? But because the river's flowing, it's taking you down as you go across, right? So we have to keep those parts separated. Yeah, Emily?
Oh, why aren't you using 20 degrees for the last angle and doing the same thing you did with sine and cosine?
Why am I using what?
Why aren't you using, well, because 100 plus 60, and then if you just use 20 degrees for the next angle?
Right there?
No, the one where it says lost.
Right here?
Yeah. Are we saying that
I mean,
one of those angles is wrong and that's what we're trying to fix?
no, I'm not trying to fix anything. I'm trying to just show you. We did a law of cosines problem here. And I was questioning this value. So now what I'm doing is I'm showing you a more powerful way to solve this same problem. Okay. Writing this in vector algebra format.
Yeah, I'm just wondering what you did with the little triangle, why you're not doing that with the...
You mean this triangle?
Yeah.
Like why you're not calculating the degrees back and doing a sine.
On this problem to get
exactly.
this or something?
Right.
Yeah, because I'm concerned about this value.
Okay.
And I'm showing you something more generalized. So what I'd like to do is I'd like to leave this on the board, but what I'm showing you what to do when you're adding vectors together is you simply write each vector in its component form. That's important. And this darn board is so small. Here's what I'm getting at. You take a vector, in this case we have this vector with its standard angle, and we're seeing that there is some distance to the east traveled. And I think there might be a little confusion. If you were on a unit circle, folks, and that was 60 degrees, you know that this would be the cosine of 60 degrees, and this would be the sine of 60 degrees. And I've said this many times in class, right? We all know this. If I keep that same direction, though, and I make that length 5, then doesn't that just scale the triangle up in size by a multiple of 5? So that leg is 5 times the cosine of the standard angle, and this leg is 5 times the sine of the standard angle. That's very important. So we have traveled to the east this distance, haven't we? Everybody should feel good on that. We've traveled east that far, and we traveled north this distance, haven't we? Okay, now we are then at this other spot up here, and now we're going to travel this distance, 16 miles, and it's the same kind of a thing. Here's our standard angle, 340 degrees. How much of it is further to the east?
5.
No, not 5. This 16 cosine of that standard angle. Does that make sense? How far south did you come? 16 sine of that standard angle. And what I love about the standard angle, folks, and you've learned this ever since you started with the unit circle, is the sine of 340 degrees is negative, right? On your unit circle, think about it, the sine of 340 degrees is negative. So what's automatically built in here is the fact that this value is automatically calculated as a negative, which brings you further back to the south. If north is positive, then you're now traveling back to the south, that distance, aren't you? And it's the sign, the plus or minus character, is automatically built in if you always use the standard angle. Okay, back to the algebra. So now, here's vector A in component form, the east and the north, and then we're adding to it 16 cosine of 340 degrees and 16 sine of 340 degrees. And that's going to yield our resultant vector for us. So we're going to end up with an x part of the resultant, comma, and the y part of the resultant. And at this point, let me get the door. At this point, we can efficiently use our calculator by doing the following. 5 cosine 60 plus 16 cosine 340, and store this in memory cell alpha x. Something's wrong. Oh, I see what it is. You see my mistake? I mean, isn't that garbage? Look at the physics of the situation. Look at the physical situation we just played with. This is totally garbage, isn't it? This result? What's my mistake? I forgot a parentheses right here. Okay? Once again, a good example of using your calculator or using your brain in a sketch to come by and catch those kind of things. Now, does that look better? I hope so. So 17.5 miles approximately to the east. To the east. All right. Now I'm going to show you a trick. Or it's not a trick, it's just efficient. It's just efficient use of your calculator. So what we're picking up here then is a 17.54 approximately miles to the east as a part of the resultant. And then all I'm going to do now is notice the math. The math on the y part here, or the north-south part, is identical except for the change in the trig function. So what I do is I replay this expression on the calculator. I replay this expression on the calculator by going shift. I hit the shift key, you can see it here. And I hit the enter key, which replays that expression, and I simply step back in here and change this to sine, and come over here and change that to sine, and I come down here and change this to alpha and y. And we end up with a negative 1.14. So here's what we get for a vector resultant. So notice that we're only about a mile south of the starting point. We're only about a mile south of the starting point, and we're 17.5 miles off to the east. East and south, right? Because the y stuff is our north-south information, and the x business here is our east-west information. Any questions so far? Okay, at this point, we want to draw a picture of this resultant. Because if you look back at my original sketch, I drew it where my r was actually sitting above the east-west line from our starting point. So what's really going on, I'm just going to come back here and make a slight adjustment on my sketch. Here's our, so this is actually down here. And so here now is the resultant vector, slightly south of the horizontal east-west line. Okay? So we have then a vector for our resultant that is 17.54 and just a 1.14 to the south. So here's the way that resultant is drawn. And if I then go and find this angle right in here, if I find this angle right here by going inverse tangent of the y stored value over the x stored value, I go inverse tangent of alpha y divide by alpha x and store that in alpha theta. You even have theta on your calculator available. It's down on your number 3 key. Minus 3.73 degrees. And how far are we from the starting point? How far are we from the starting point where we're lost? Pythagorean theorem on these legs. And again, these were stored in the memory of the calculator in memory cell X and memory cell Y. So the magnitude is going to be the square root of the sum of the squares of those legs. And I think I'm pretty darn sure that our Pythagorean theorem, or our work we did earlier with the oblique triangle, is still going to be okay, but I'm going to check it right now by going square root of x squared plus alpha y squared. And I'm going to store it, and I'll just hit it. And there's the same value, 17.6 miles coming out, which agreed with the earlier work, even though my scaling was a little bit off there. Do you see the power of the vector algebra approach? What do you do if you had 5 legs on your hiking trip? Just line them up and add them up and use the memory cells of the calculator. Easy. Not bad. Okay. Let's go ahead and stop this segment, and then we'll do a little bit more in a couple minutes here.